All right. Well, we'll go ahead and start here. There is there we go. So those we've all mostly gone through, just more practice, right? Yeah, and that's the one that we talked about on the board. Actually, I don't, is it the same one? The practice, yeah.
Yes.
So it cuts it in two places, but other than that, it's pretty straightforward, like we talked about. I'll let everybody. We'll go through those next Tuesday. Just if there are any other questions, once everybody's had a chance to finish it up. So this is sort of the training wheels on synthesis. It's shown as one arrow, but really this is going to be a series of reactions. What are the series of reactions? They're going to take us from A to B.
Right. So I started off with elimination.
Good.
And then WT with E.
Yeah.
And then from there, hydrobromation or carbon.
And that goes from here.
Yeah, and then another elimination, giving the same set of products, which we are looking for. Yeah,
Good.
I have on there.
Yeah.
And from there, hydroboration.
Yeah, the anti-Markov-Makov.
To get the anti,
Hydration.
So that one was.
And that matches the stereochemistry here too, right? Because it would be the OH and the hydrogen add syn relative to each other.
Right.
Which would put the OH in the methyl trans.
Right.
And the enantiomer. So good. So then.
It was B that was the visualizing it kind of thing.
Right.
So that for I said TB okay for the elimination to try to hinder sterically, right?
Right.
And put the 5 on where it's giving you the Hoffman product, right?
Would put the 5 on here, right? So that would be giving us norbornene, which we didn't see in lab on Tuesday, but we'll see next Tuesday. That norbornene is this bicyclic with the 5 on there.
Yeah, and then I said ozonation from there to split it right there.
And that gives you the 5-sided ring here, plus a methyl with the carbonyl and a methyl with the carbonyl. And that's this guy. So yeah, this one is with these bicyclics, a lot of times that is the trickiest part of it, is visualizing it. So recognizing that this is a 5-sided ring,
right,
is the key there. If we wanted to leave a 6-sided ring, we could do something different where we might have to do something like this, where we move the pi bond over to this other side.
right.
And there's so much steric hindrance with this one that who knows whether that would actually work in practice, because with this being such a constrained structure, some of our normal tools for moving pi bonds around. And getting the Hoffman product and things like that might be a little bit tricky, but we could still do it on paper.
Yeah, that's what I was worried about, is the actual, but whatever.
Right, I mean, all we can do is propose them at this point and then see if it would actually work, right? And take into account everything that we're able to. All right, and then the last one was.
It's 2 more.
Oh, 2 more, yeah.
Yeah, compound X, C7H14.
So hydrogenation gives 2,4-dimethyl pentane.
Oxidation is alcohol.
Gives us alcohol. And so that'll tell us where the pi bond was, right? So the first one, the hydrogenation, is going to give us our carbon structure. our carbon skeleton. But we still don't know, just based on that, where the pi bond was, but the fact that the hydroboration gives us the anti-Markovnikov, and it gives us the 2,4-dimethyl 1-pentanol. So if that's the anti-Markovnikov product, and the pi bond had to be right there.
Gotcha. And the acid catalyzed.
And then, so it's a major product when treated with aqueous acid. So acid catalyzed hydration gives us the Markovnikov, so same. No rearrangement to worry about in this case, because it's already a tertiary carbon. So we get the 2,4-dimethyl 1 or 2-pentanol. And it would be R plus S. Because this is gonna be, no, it's not a stereo center anymore, is it?
It's got.
Yeah, yep.
This was the one that was visualizing as well, because it was the acid for the mechanisms.
Right. So one step at a time, we know that this is gonna make an epoxide, right? And that has that weird 5 arrows at the same time.
The transition state.
Yeah, exactly. So the main thing is if you start by drawing out your pi bond. And then we know it's the OH. It's gonna give us the oxygen, right? So in order for this to work, what's gonna really happen is this carbonyl is gonna turn into an OH by grabbing the hydrogen over here. And in doing so, that gives this oxygen, or this pair of electrons, pi electrons here are gonna shift over to this oxygen. And we wind up kicking this oxygen off. So in the trick with anytime you've got where an oxygen single bond, almost always the reaction that's gonna happen is that oxygen single bond is gonna break. So that's one of the ways we know it's gotta be one of these two oxygens that's gonna be given away, is because that's super unstable.
I was missing the oxygen.
Yeah, so we're gonna have this move that way. These electrons go there, these electrons come over there to give it the epoxide. So that was a whole bunch of electrons moving at once, and I think I probably threw some of these arrows the opposite way as in the mechanism we actually looked at.
For the oxygen to oxygen single bond, would they separate the electrons?
Homolytically. Where one electron goes each way, not in this case. If we have just a true peroxide instead of a peroxy acid, especially if we shine light or heat it up, then we should be looking at a homolytic cleavage and a free radical reaction. Usually peroxides, that's the mechanism we're going to see more often than not is going to be a homolytic free radical mechanism. In this case, however, it goes through a slightly different pathway. Peroxy acids are slightly different than pure peroxides. Mostly because they have this ability to make this sort of 5-sided transition state. And so then that's gonna. And the main thing is, if you're not sure if you drew the arrows facing the right way, look at it and say, okay, well, as long as I didn't draw any arrows coming from nuclei, because we never want to show the nuclei moving, we're always showing electrons moving towards nuclei. And I think I was okay with that. This is going to turn into a lone pair.
this is gonna turn into a pi bond here. Sigma bond to the hydrogen, these electrons move to make an oxygen carbon single bond. These pi electrons make the other oxygen carbon single bond. So while for whatever reason, it's looking to me right now, and it could just be that I'm still a little bit out of it. It's looking to me like I may have done some of those arrows backwards, but I can't find an error with it right now.
Fair enough.
And it gives us all the bonds that we know we're gonna be making. All right, so step one is just that, and it's a one-step mechanism with a whole bunch of arrows. Yeah,
That's like a counterclockwise kind of movement of all the.
yeah, and that's why this one doesn't, I guess, it mostly seems. Oh, you know what it is? We could redraw this one. To show. Pi electrons moving to the carbon and these electrons moving to be a lone pair. Same net result, but that keeps the electrons going in that counterclockwise direction.
So we have 6.
We have 6 arrows, we still didn't. And it is the same net result, it's. This just makes it look a little bit cleaner. I think either of those I would accept as a full credit answer on a test, especially. Yeah, the main thing is because in these transition states where we tend to have a whole bunch of arrows happening at the same time, a lot of times we'll see that pattern where they tend to be moving in a circular direction where everything's kind of moving the same direction. Right, kind of like just a current. It's not actually how it works. And so, because this is just all orbitals, you can have them moving opposite directions, but this keeps that theme. So this looks a little bit better to me, even though it's one extra arrow to draw. And actually, I guess we do have to do that, otherwise we'd wind up with this oxygen. The way I drew it before, we'd be taking a pair of electrons away from this oxygen. And leaving it without a full valence. So this is better. And then we get this as our product, and then the second step is just that ring opening, just SN2 and the leaving group leaves. It's just that the leaving group is part of the same molecule still, right? So it starts with it's an acid catalyzed ring opening. So we just have I'm not going to draw the whole molecule because really we're just going to show that bond breaking and then a pair of electrons grabbing the hydrogen. So we do get a intermediate that's going to look like the same molecule just with the oxygen protonated. And we would get the enantiomer for this one as well. So I've drawn these with the oxygen, the epoxide pointing up towards us. Just as likely to have the oxygen pointed down. So we will get the mirror image of this as well. I'm just not going to write EN the whole way through. I'll wait to the end. So I just write that once. Okay, and so that's a positive charge on the oxygen. We know that's not very stable. And it also makes an oxygen with a positive charge is a really good leaving group. It's how we do elimination reactions when we have an alcohol. It's how we do elimination reactions. Anytime we have an oxygen that we want to be a leaving group, we protonate it. And then the second step is we've got ethanol as our nucleophile. So instead of an oxygen coming in from a water molecule to get a dihydroxylation, we're going to get an alcohol group on one carbon, and we're going to get an ethoxy ether, an ethyl ether on the other carbon. So. And out of these two carbons, which one is the oxygen gonna be attracted to?
Less substituted.
We would think that normally. Because we don't use SN2 on tertiary carbons usually, right? It's actually gonna have a preference of this bond, the bond between the oxygen and the carbon is weaker on the more substituted carbon though. And the reason that we can still do an SN2 on a tertiary carbon is it's not a true tertiary carbon in terms of geometry. Because it's got this strained ring structure, it is still a little bit more polar than it normally, or more planar than it normally would be. So it does go through, it's still Markovnikov-ish. Where we're gonna come in and attack the more substituted carbon because that's the easier bond to break. And so really it's for the same reason as the mercury, as oxymercuration with Markovnikov. Because that oxygen to a tertiary carbon is a little bit weaker of a bond. We're going to preferentially attack there. And it is not a hard rule though. Like this is definitely one where it's stereoselective, not stereospecific. You're going to get, or regioselective, not regiospecific. You'll get a mixture of the Markovnikov and anti-Markovnikov rules. Or products, I mean. It's just going to favor usually putting the oxygen on the second oxygen on the more substituted carbon. All right, and so then our final product is going to be plus enantiomer exactly. Right, so with these mechanisms, the more practice you do, the more you show your steps on some of the reactions, the more you spend time sort of absorbing it. The more they're gonna feel like second nature. Like they make sense, and they will eventually, but I'll caution you against the fake aha moment. Because I definitely, the worst score I ever got on a chemistry test was in the midterm in OChem where we started getting heavy into mechanisms, because I started thinking, oh, these make sense. I don't need to memorize these because I can just like work my way through them in real time on the test. And it took I made too many dumb mistakes and it took way too long. So for now, you'll get to that point where you can logic your way through the mechanisms as you go. Just be careful on the midterm that if you're gonna take that approach, be sure that you're actually got there. Don't just be a lazy student. I was convincing myself, oh, these all make sense. I don't really need to study them because I wanted to go surfing. So don't let that distract you. Don't let the fact that they make sense keep you from studying them, because there's still stuff like this. And I've been doing this how many years and I still got one of the arrows backwards. So be careful.
You said that the alcohol on the tertiary carbon is a possible product.
Yes, so you'll get some amount of it where it goes this direction. That's just gonna be a minor product though. And usually with the mechanism on the test, when we do mechanisms, I'll give you the product that I want you to draw the mechanism for. So you're not worried about, well, do I show the mechanism for the minor product? On the test, I'll tell you what product you're going for. In this case, as long as you understand that there's also the minor product and it comes from the same process, that's fine too. And in fact, that's also another place where you can use the test against itself. Because I'm giving you the answer to a reaction problem, right? So you can go back and that might be something that triggers you remembering, oh shoot, I forgot about rearrangements on my reactions page. I gotta go back and make sure there were no rearrangements, because if you see one on the mechanism. So remember to use that to still be keeping those reactions in the back of your head when you're doing your mechanisms, because it should be a way to sort of double check at least a couple of your answers. Brad, how you doing?
3 people. That's
Only-
it for today.
Only 4 enrolled total, so. Any other questions on that paper assignment from Tuesday? Okay. Then we'll get into talking about alkynes. So alkynes are going to share a lot of similarities with alkenes. And it becomes pretty obvious to see why when we actually think about it, because it's still carbon-carbon pi bonds, right? It's not aromatic, so we're not throwing that wrench into the works here. So an alkene is 2 carbons that have a sigma bond and a pi bond. Alkyne just means a sigma bond and 2 pi bonds. So a lot of the same reactions are going to happen. In a lot of cases, it just means that they happen twice. You can still do a regular acid catalyzed hydrobromination. It's just going to happen if you do it once, you're still going to be left with a pi bond. So you do it twice. So we'll see that in a few of these where the mechanism is literally identical. You just have to repeat it once. And when we're naming these, we name them the same as alkenes, except once again, they're even simpler. In that we don't need to worry about cis and trans or EZ, because your 2 carbons in an alkyne are linear, right? So there is only one other thing attached to each carbon, so there's only one place to put it. It still has the hindered rotation, kind of, I guess, but how do you rotate something that's already linear? It's not going to really change anything to rotate it, right? So naming these, just more practice naming. So what's our longest continuous carbon chain that has the alkyne? So our longest continuous carbon chain, you can look at it and see it's just straight left to right, but it's got to be the longest continuous carbon chain that contains our important functional group. So, yeah, it goes this way, right? 1, 2, 3, 4, 5, 6, 7. You might notice that drawing the skeletal structures for these gets a little bit weird too, because it's linear. When you draw it linear, it can be hard to tell. And so you'll notice this one actually has a complete break in between the alkyne group and the rest of the carbon chain. That's just to make sure that you know that that's actually a carbon right there. So it's 1 carbon, 2 carbons, 3 carbons, even though it's a straight line. The other way that you see that done is just draw out that part of it and then make the rest of the molecule skeletal, just as a way to make sure. And then we do so that's really kind of a bastardized mixture of complete structure and skeletal structure, which I don't know if you remember, but we actually had a name for that, where we did part of the molecule in skeleton, condensed structure or complete structure. That was the Kekule's version. There's an accent on one of the E's, but I don't remember which one. That one maybe. Shut right. So this is a total, even if I ask specifically for skeletal structure, this is still acceptable in the case of Alkynes, because we wanna make sure you see that. Otherwise, it's really easy to. How many carbons is that? It's kind of hard to tell because they're all in a straight line. Right? And how do we name this? Well, we've got, it's gonna be heptine. Right? One heptine. Or heptwanine, if you wanted to. I don't like that. Brad doesn't like that. And then, yeah, we've got 3 propyl, 4 ethyl, 5 methyl. And there's some stereocenters in there too, but we're not given enough information to know which specific stereoisomers. Because that's gonna be a stereocenter, that's gonna be a stereocenter, and that's gonna be, so we actually have 3 stereocenters here. But since I don't give you enough information, just name it like they're not stereocenters. So. 3 propyl. 4 ethyl. 5 methyl. And just a reminder, the number that we care about keeping the lowest. Is the one that gives our molecule its primary name. So we care the most about keeping this number low. Even if we could count from the other end and we'd get these ones lower. Whatever you name, whatever goes last in the name, whatever functional group goes last in the name has priority. So that's the one we care most about keeping low. Nomenclature's getting to be a little bit easier, right? You might have scoffed when I said back last quarter that eventually nomenclature was gonna be your safety blanket, like, oh, it's nomenclature, that's so easy. But we're getting there. And just like I mentioned before, if we have alkenes versus alkynes. Alkenes have got a carbon-carbon sigma bond where we've got direct overlap. And then a pi bond where we have that partial overlap, where these unhybridized p orbitals will spread out to make those sort of canoe shapes. Or sometimes no, that's a different term. I can't call it. They're kind of banana shaped, but they're not banana bonds. That's a different thing. So canoe shaped, go with canoes. And an alkyne is the same thing, just with 2 of those pi bonds. Right, so that actually means we have 2 pieces of the p orbital that are not hybridized. So what is our hybridization on an alkyne? Just sp. Okay, we have 2 electron domains around that carbon. So we only have 2 hybridized orbitals making sigma bonds. And just like I already mentioned, still just carbon-carbon pi bonds, right? So it's going to go through a lot of the same reactions with a couple of caveats. There are a couple of things where one, it could happen twice, or there's a couple though where it doesn't happen twice. It, like for example, we'll hydrate and get it one step where we get an alkene with an alcohol attached, but an alkene with an alcohol attached actually isn't very stable and it rearranges itself to be a carbonyl. So it's still the same mechanism, just with a rearrangement tacked onto the end. If we want to make an alkyne, basically, if we wanted to make an alkene, we would just take an alkyl halide, give it a strong base, and we do an elimination, right? We want to make 2 pi bonds, we just do a double elimination. My wife and I have been watching Top Chef for literally decades at this point, and it's always like the dramatic music comes in and say, this will be a double elimination. Exactly. In this case, our double elimination is exactly what it sounds like. So we can actually go from an alkene to an alkyne pretty easily too. Right, because if we started from an alkene. We can do a dibromination, right? Add a bromine to each carbon, just by adding bromine Br2. And then that gives us two things we can kick off. So it takes us 2 steps to go from an alkene to an alkyne. Halogenation followed by double elimination, but that's not really particularly hard to do, right? The key with this, there's a couple keys. One, the stronger the base, the better your yields are gonna be with the double elimination. And also, you also need to watch out for your stoichiometry. If you're gonna have it go through 2 eliminations, you've got to make sure you've got 2 equivalents of that base. So it's got to be able to pull the hydrogen off twice. And you'll usually see that in the reaction. We'll say 2 ETOH or 2 NaETO. The most common way though is takes care of both of these issues at once. You just use an excess of a really strong base, sodium amide. You start by doing the double elimination. But then it'll actually go 1 step further. This is a strong enough base that'll actually deprotonate if it's a terminal alkyne. And when I say terminal alkyne, I mean at the end of the carbon chain. So if we have a hydrogen attached to our alkyne, that's actually fairly acidic. If you get not that acidic, it's more acidic than most alkane hydrogens would be. We still have to use a really strong base to get there. But what that allows us to do is that actually turns this into a nucleophile. So we just added ozonolysis as a way to break carbon-carbon single bonds so that you can cut down the carbon skeleton. This is going to be a really good tool for building up the carbon skeleton. We want to add carbons. We can just turn our molecule into an alkyne, deprotonate it, and now this carbon is a nucleophile. And because if it's not a terminal alkyne, we have this molecule, for instance, 2-butene. If this is in the presence of that excess amide, it'll actually rearrange itself to turn itself into the terminal alkyne so that it has a proton it can give. With a strong enough base, you can actually force it to rearrange. So in general, when you add excess sodium amide, not only are you going to go through a double elimination, you'll also kind of force the pi bonds to the end of the carbon chain. And then if you then just added some water to it, that's enough that it will protonate and you just wind up with your terminal alkyne. If instead of just adding water, you added something with a good leaving group, something that would be a good target for an SN2 reaction, we're just going to have this act as an SN2 nucleophile. So, does it matter if the 2 leaving groups are on the same carbon or on adjacent carbons when it comes to the double elimination? No, it doesn't matter. We're either going to have our leaving group leaves and pull off a hydrogen here, and then leaving group leaves and pull off hydrogen here, or leaving group leaves and pull off a hydrogen here, leaving group leaves, pull off a hydrogen there. So we're pulling hydrogens off of different carbons based on that, but our net result is still make the terminal alkyne.
Even if they're opposite ends of the curl field.
No. So when that, there's limits to that rearrangement, and basically it's. You still have to be able to have them close enough that they're on adjacent, your halogens have to be on adjacent carbons. Maybe as far as 2 carbons away, but for the most part, you'll see it like this. I would actually have to go do some digging and double check if they could be 2 carbons away, because you're intermediate in that case. If you put this in the presence of another super strong base, could it go through a rearrangement in the process to put the 5 on the same side? Maybe. I'm not gonna give you one like that on the test.
Something like that.
Yeah. That's a good question, but yeah, there are limits to this, and this is all kind of, I'm giving you general rules. And there's gonna be limits to that. So what do we get for our product for A? Still, the carbon skeleton is gonna look a little different because we're not drawing it at 120-degree angles anymore, but we still have the same number of carbons. It's just that now we're gonna add a 5 on there, or 2 5-ons there. So it'll look like this initially. And then our second step is we just added water. The water is not gonna act as a nucleophile in this case because we actually have an abundance of electrons. We don't actually have a good target for a nucleophile. It's just gonna be a proton source. So that we're gonna get. We're just gonna probe. And I believe this gives us the same molecule, doesn't it? 3,3-dimethyl. 1-butene.
Yeah.
That's the other thing about these, when you draw them out. It's the same error or same issue we've been talking about. Is when you're finding your longest continuous carbon chain, be really careful to remember that there's 2 carbons there.
Would be wrong to put in neighborhood, I mean, to know if it's gardens there. I know that it's linear, or it's pointed at the.
You don't see it done very much. So I would prefer if you drew them linear. Just for the sake of it more accurate to reality. 109, if it's tetrahedral carbon versus an sp2 carbon, 109 degrees versus 120 degrees, those are close enough that we can draw them as being the same. Most of us can't tell the difference by eye of 10 degrees off anyway. But 180 versus 120, that's a big difference. All right, and as I gave you the preview for, if we make an acetylide ion, and actually they're technically they're called alkynide ions. I tend to call them all acetylide. Technically, an acetylide ion is this. The IUPAC name for this would be ethyne, but the common name for it is acetylene. You deprotonate acetylene. That's an acetylide ion. Technically, if this other one is an R group, it's technically alkynide. Basically, just drop the E from alkyne and put an "ide" on there to show that it's got a negative charge. I tend to call every alkyne that's been deprotonated, I kind of tend to call all of them acetylides. It's not technically correct, and that's not even probably a common thing.
Why is it
Um,
not set a line?
Why is it not pronounced that way?
Why?
It's just because before we had IUPAC, it was the Wild West. So it's just an old common name. And the old common name for ethene didn't even match that either, it was ethylene. And then you had acetylene, which was ethylene with an extra pi bond. So just because it's old, it's a molecule that's been around for a long time, like acetone. But all this to say that if you hear me say acetylide, where you can put it on slide like that, that's technically incorrect. That's just me, not paying attention and using the way that I think about it. It should say alkynide. This, however, is acetylide. So I guess technically this slide is not wrong because of this exact sample in the figure here. And that just means it's a pretty good nucleophile. It's not sterically hindered most of the time. You've got a pretty good, strong negative charge that in a carbon with a negative charge is not particularly stable. So it's going to find something it can react with pretty well. It's a better nucleophile than an oxygen with a negative charge. It's not as good a nucleophile as hydride or amide. These, remember, the stronger the base, the better the nucleophile it is too, barring sterics. And that's why we have to use the sodium amide to deprotonate this. We can't use these to deprotonate our alkynes, just because they're not strong enough bases. And so that also opens the door to us taking a terminal alkyne and using it to add carbons. So we'll go through this slide and then we'll take our break. I should ask when you walked in, did you have anything you were announcing or you just coming to hang out?
I was just seeing when you were done, but I couldn't turn away.
I appreciate that about you, Bradley. All right, so if we've got our excess, it doesn't say excess in this case, but it's already an alkyne, so we only need one equivalent of it. We're going to deprotonate our alkyne and then use it as a nucleophile. So by doing our steps this way, we have ethyl iodide or iodoethane in our second step. So basically, this is going to be the target for our nucleophile. First step is we're going to turn this into a nucleophile and then have it go through an SN2 where that iodide is attached. So first step is going to look like this. And then we have our iodide leaving group. So we had 1, 2, 3, 4, 5 carbons. We're going to add 2 more carbons to the other end. So our final product here would be 1, 2, 3, 4, 5. And then we're adding 2 more. 1, 2. So typically, because we don't need to worry about rearrangements as much this way, the way that you put an alkyne in the middle of a carbon chain is to start with an alkyne at the end of a carbon chain and then just add however many carbons you want to the other side. Right?
So now if you wanted to go from that to an alkene, could you just put it in the presence of water? Or would you need something stronger?
We'll need something stronger. We could do hydration reactions, but alkynes don't work very well with just acid catalyzed hydrations. We're gonna have to either use hydroboration or oxymercuration. Oxymercuration is more common Because we're not actually gonna see a difference in terms of Markovnikov, because both carbons. Are gonna have two other carbons or one other carbon attached to them, right? So we'll talk more about the specifics of what we can do from there. After we take our break. If we start from acetylene. C2H2. Deprotonate it, put it in presence of. Iodoethane. Same thing happens, right? We just started only with two carbons. So we're still gonna have our acetylene carbons. And we're adding two more, 1 and 2. So actually starting from acetylene and having access to some halogenated alkanes. We can actually build the carbon structure up with a lot of specificity. To make it however many carbons on, because there's nothing stopping us from then doing it again. If we added step 3. NaNH2 again, followed by. Another iodo, let's just keep it the same nucleophile or the same. Molecule. Then we're gonna add 2 more carbons to the other side. So acetylene, this is one of the reasons why it's such an important molecule. It's not just because we can burn it in welding gas to cut stuff. It's also because it's a really important building block in terms of making all of these pharmaceuticals from scratch. Starting from a natural product and adapting it works pretty well sometimes. If the product we're trying to make is close to something that you can economically harvest and extract. But if we're trying to make something that doesn't occur in nature. A lot of times we're gonna start from a raw feedstock of just acetylene. And halogenated alkanes. Build the carbon structure up the way we want it, rather than having to deal with. Growing something, harvesting it, extracting a natural product, purifying that, and then doing some synthesis steps. There are some times when that's helpful, when we're trying to do, like, if we just wanted to make a chlorinated eugenol, starting from eugenol is a pretty good way to do that. But. If we don't have a really good source of it naturally. Or through agriculture. Not all plants can be grown in an agricultural setting equally well, right? Some things it's just not very economical to do. Which is one of the reasons why. Even. Chemists across the board are pretty united in. Understanding and promoting getting away from fossil fuels. Other than as feedstocks for all of these molecules that we're developing. That the chemical and pharmaceutical industries would have a huge shakeup as well if we went totally zero oil. Because acetylene and a lot of our precursors that we use come from petroleum. Are their number one process or place that we get a lot of this. So that's a drop in the bucket compared to the amount of petroleum and carbon that we burn. In driving cars and in generating power. But it's still a significant thing that if you go into chemistry, that in the next 10 or 20 years, you're gonna see a dramatic shift. Because all of our feedstocks are gonna change. As we have less and less oil.
This process seems like it could be very selective what you want to make, if you just keep on doing stuff.
That's exactly right. Yes. Because once we have it, especially once I add in the addition reactions we can do with alkynes, we could get rid of the alkyne here, but then halogenate it and do another double elimination and put another another alkyne at the end over here. And then repeat the whole process. So there's really it's one of the more powerful tools. When it comes to changing your carbon skeleton, ozanolysis is a really good one because it's really predictable, really easy to use. When it comes to building carbon skeleton, this is one of the main uses or main reactions we use. This and Grignard, which we'll add into this chapter, couple chapters after midterm, we'll talk about Grignard. All right. Oh, I didn't even realize. We had steps 3 and 4 right here.
to make the point I already made. If we took this and then deprotonate again, except then used methyl iodide instead of ethyl iodide, we'd add one carbon to the other side. So like you said, there's a lot of options, a lot of flexibility, especially if you've got a decent selection of halogenated alkanes, which turns out aren't that hard to make. If you have the alkane, making a halogenated alkane is a quick free radical reaction that actually has pretty good yields. You just get a mess of all the possible products that you then have to purify. But that allows you to basically get a good leaving group on any molecule.
So does the leaving group matter?
Whether it's iodine or bromine or
Yeah,
not really.
it doesn't matter like in synthesis for like yields.
So iodine is a better leaving group
Mhm.
than bromine. So you tend to get even better yields. The other reason that iodine gets used, especially on small molecules, is because iodoethane is a liquid, bromoethane is a gas. So it's more for
Yeah.
practical concerns. It's a lot easier to add a liquid than it is to do a gas phase reaction. And it's just because larger the halogen, the heavier it is, the more intermolecular forces you have.
Yeah.
So higher boiling points. But yeah, really anything chlorine, bromine, or iodine will all go through the same process pretty well. And in theory, other leaving groups too, but you'd have to, protonate the oxygen to make it a better leaving group, which then is gonna give you a lot of trouble when it comes to taking this molecule. If you're in an acidic environment, you can't really take this molecule and add it in very well. So you'd be better off turning your oxygen into a halogen by doing an SN2 and then following that with your acetylide as the nucleophile. All right, let's take a break there. Let's do 10 minutes. Let's come back at 5 after. How can I help you, Brad?
Well, I couldn't make it on Tuesday or yesterday.
Oh, to ours.
Yes.
That's okay, I'm gonna hold on to the weather anyway, so.
I can wait if you wanna take a break yourself, come back later.
No, it's fine.
Well,
You wanna do this?
No, it was, someone wanted me to try to find a free version of textbook. But yeah, $300 for one fucking book.
I know, it was like 300.
That's pretty nice. Well, Ben, I've just got a headache at this point, but. Are you looking for me or?
So this is the physics lab now, although I think they're still mostly in the chem lab. But you know where their office is, you came in down that hallway, right? All right, perfect timing. All right, so let's talk about other alkyne reactions. The ones that we're just porting over directly from alkenes. Hydrogenation, hydrohalogenation, so with HBr. And halogenation, so with Br2. And again, these all mostly work with chlorine as well. We don't see them as often with iodine. They tend to be a lot slower, especially just straight I2. We don't dihalogenate or diiodinate. With HI, hydrohalogenation maybe, but either way. And really it's just, you do it twice. So our same rules from our Markov apply, our same rules for, I know that's a big one, world students, yeah. And sin versus anti, and that'll even matter a little bit less because there's no anti. Wait, it's linear,
Yeah.
so.
No, you can put it like that.
Right. If we do this. If we do our hydrogenation, I have a slide on each of those three with some of the specifics because they're a little bit different. If we do this with two equivalents of hydrogen, so if we take acetylene, do two equivalents of hydrogen over platinum, just like we did with alkenes, we get close to 100% yield of ethane. So we can hydrogenate as long as we want to double hydrogenate, we can do it pretty well. But because this process is based on and on these molecules absorbing the platinum surface, the molecules that start to react, if we tried to just use stoichiometry to do this, to do one hydrogenation, to take it to ethene, we actually don't see that because the molecules that are absorbed onto the platinum surface are too reactive once they start reacting. So if you try to do it with one equivalent of hydrogen, you get 50% unreacted acetylene and 50% fully hydrogenated. So we can't really stop it at ethene just by controlling.
So it has to go all the way to ethane. just because
exactly.
it's so reactive with.
Exactly. It's, so we actually use a different tactic. We can hydrogenate just one of these pylons. We just have to change the catalyst. We actually change the catalyst so it's less effective as a catalyst. And that allows it to slow down that second step enough that you can actually get one equivalent of hydrogen reacting. And so they use that, they call that a poison catalyst. Very descriptive name. The poison catalyst just means it's pretty good as a catalyst, but it's not so good that it takes you all the way. So you actually, even if you have excess hydrogen, you can't fully hydrogenate. It'll stop at the alkene if you use a poison catalyst. So the alkyne is reactive enough that the poison catalyst works, but the alkene is not reactive enough for the poison catalyst to cause it to react. So the most common one, and I had it wrong, I think I said rainy nickel is a different one. Lindlar's catalyst is the poison catalyst that gets used. I believe I do believe it has nickel in it, it's an alloy, it's a couple different metals mixed together. Oh wait, here it is. Palladium treated with calcium carbonate and trace amounts of lead chloroxide. So palladium's a decent catalyst on its own, but if we mix it, we put a little bit of carbonate down on the surface and mix it with a little bit of lead oxide, you get kind of a barrier to get into the palladium that causes it to stop the reaction halfway. And because this winds up being, when we talk about hydrogenation of alkenes, we said because it happens on the surface, you only get the syn addition, right? Well, we don't have to worry as much about syn addition because it's linear, but it means we only get the cis product. We don't get trans out of our alkene that we make here. We do have a way of making the trans alkene. But it's a lot nastier of a reaction. It's called the dissolving metal reduction. So this is not ammonia in a solution, this is liquid ammonia, which boils at a low temperature and is really nasty. So liquid ammonia with solid sodium metal. And it still only gives you an 80% yield. So one, you've got to keep it really cold. Two, you're dealing with solid sodium metal, which we remember the demonstration from Gen Chem, what happens when you put sodium metal in water. And you're dealing with liquid ammonia, which is really nasty. So less ideal. Which is okay because for most pharmaceutical applications, the trans alkenes don't show up in nature very much. So very rarely do we actually need specifically to make the trans alkene anyway. And so for the most part, it's totally fine to use the Lindlar catalyst. And like it shows here, it'll just say Lindlar's catalyst in the reaction conditions instead of PT or trying to write out palladium, calcium carbonate, and lead oxide together. Just call it Lindlar's catalyst. So we went through a series of reactions. We've got two bromines, which means we can do our double elimination, right? And we have excess of sodium amide.
So excess.
Exactly, seems the same thing. When you're short on space or feeling lazy. I don't know if the members of the band in excess
from the UK actually took chemistry or anything, or if they just abbreviated it that way because it looked cool. But in excess was a new wave band from the UK. Actually, usually with a star, I think. Means, but all this means the same. So we do our double elimination and deprotonate our alkyne. So first thing we get from the excess sodium amide. We make the alkyne and then deprotonate the alkyne, make the alkynide. And then we expose it to ethyl chloride. So we're gonna add 2 carbons onto the other side of the alkyne. Now we're sitting here, and then we can follow that up with Lindlar's catalyst. And hydrogen to get this molecule. David, I know you're gonna go back and watch the recording, but just so this makes sense to you. And we can deprotonate an alkyne, terminal alkyne, turns it into a nucleophile. We just do an SN2. Exactly. So that's our new way to add carbons to a carbon skeleton. And we're gonna start seeing, as we add more and more types of reactions, especially reactions where you can make a functional group and then use the functional group, we're gonna see reaction series like this a lot of times. And it really, it's the same as, it's just them happening in sequence. This is just a convenient way to write them out. Still probably helpful a lot of times to show your intermediates, so you can follow through the logic, but it's a lot more compact way for me to ask questions at least.
Very good.
Yeah. Okay. All right, so the other reactions that can happen, that just happen twice. Hydrohalogenation and halogenation. There's no trick to them, they just happen twice. So we had this molecule, and we're gonna plus 2 equivalents of HBr. We're just gonna do our acid catalyzed bromination, hydrobromination twice. Nothing tricky about it. If we were doing just halogenation, so with 2Br2, we're actually gonna add 4 bromines. And actually, I guess this will go through a rearrangement. So if it's acid catalyzed, we're gonna make that intermediate, where you'll actually wind up with them both added to tertiary. So I messed that up.
Both adding to the tertiary?
Yeah, because the first thing you're gonna do is put a positive charge there, which is even less stable than a secondary. So you'll move hydrogen over, and then it'll repeat the process the second time, actually, in this, I gave you an exception case.
Yeah.
I didn't mean to do that. Because the second time, once we put one bromine here, there's not another hydrogen to move over. So the second time would actually keep the bromine on us. If there were two hydrogens to move over, it would rearrange twice.
If it wasn't.
Yeah. So we do still have all the same wrinkles to worry about with alkenes and alkynes. The fact that they can happen sometimes, that's one of the new, it can happen once but not twice if you run out of hydrogens attached, for instance. And like I said, halogenation, you're gonna wind up doing, if you do that twice, each halogenation adds 2 bromines. So that actually would give us a total of 4 bromines added. Because we'd add 2 bromines here, or bromine here and a bromine here. And then we would do it again. That's one of the ways you can make things like tetrabromoethane. There are some halogenated small carbon molecules that are really useful for things like refrigerants, but also things like dry cleaning liquid. They call it dry cleaning not because it doesn't involve liquid, but because it doesn't involve water. And so I believe they actually use a tetrachloroethane. They use some ethane with a whole bunch of halogens attached to it. I don't remember the specifics. Because that makes it heavy enough that it's a liquid and it's a decent non-polar solvent, so it's good at removing stains and things like that, but it doesn't ruin things that are sensitive to water because it has no water in it. It's to people that not taking organic chemistry, the idea of a dry cleaning liquid seems contradictory, right? But we know that liquids can be dry, it just means no water. Metals can be liquid. Metals are not water. All right. Well, now I'm thinking about that. Metals are not very good at dissolve. There might be some stains that actually you could treat with mercury, where you would actually pull stuff out that'll dissolve in a metal better than it will in a non-polar solvent.
Such a word.
I'm not aware of it being used currently, but that doesn't mean that it doesn't happen or that it's not used. All right. The 2 reactions specifically that are similar but different is ozonolysis still works with an alkyne. It even goes through the same mechanism almost. Except that it turns into 2 carboxylic acids instead of 2 carbonyls. Because no matter where your alkyne is, whether it's at the end of a carbon chain or in the middle of a carbon chain, if you break all 3 of these, you have to replace all 3 of those bonds. And because this is an oxidation process, ozonolysis, you wind up adding all carbon-oxygen bonds. So breaking all 3 of these would give us our R1 and so in a lot of ways, ozonolysis of alkynes is actually going to be easier because the molecule itself can't be as complicated. Because 3 of these carbons bonds are directly attached to the other carbon here, so you can't really have an alkyne in the middle of a ring. You can, but it has to be about 9, it has to be 8 carbons or more. You can have cyclooctane. Cyclooctane, if you did this, if you put it through ozonolysis, you would just get 8 carbons with a carboxylic acid on each end. But other than that, if there's only so much we can do, if 3 of a carbon's bonds are attached to the same other carbon. It's, you know, it's not gonna give you that many options for what you can do when it comes to ozonolysis. Cut it in half, turn all 3 of those bonds into oxygen bonds for both of them. So that was on. And hydration, we're really only gonna use one type of hydration with alkynes. So as opposed to alkenes where we had 3 different varieties, Markovnikov, anti-Markovnikov, Markovnikov with rearrangement. With alkynes, the hydration is slower, so we kind of combine the acid catalyzed and the oxymercuration into one mechanism. We use the mercury kind of as a catalyst. In addition to doing it under acidic conditions. And it still is gonna go through a very similar intermediate. Except that these carbons are sp2 instead of sp3. And so it's even more strained, and so you actually get this sort of resonance structure. Where it kind of like, it's such a weak bond between the mercury and the more substituted carbon. That it kind of like, it's there and it's not there, it flickers in and out. It's like half of a bond. It's borderline just intermolecular forces at that point. And then so this one in particular is called a mercurinium ion. And then the second step of this, once you have that mercurinium ion, we wind up with our, that's not actually shown. If we have water coming in here acting as a nucleophile to the more substituted carbon, so it's still gonna be Markovnikov. And then we're gonna make this as our intermediate. So then we still have to go through the demercuration part. So a quick proton transfer breaks the second pi bond. To add the water to the same carbon as the mercury. But then that leaves you with a carbocation. So you wind up making a resonance structure where the oxygen winds up making a sort of a temporary carbonyl, but then the more stable way to do that is if the carbon just steals the electrons back from the mercury to remake that pi bond. So the end result of this, the end result of this slide is we broke one of the pi bonds out of the 2. So we hydrated one of the pi bonds, but not the other. All right, so make your mercurinium ion, attack the more substituted carbon with your nucleophile. And then just do a little bit of rearrangement to kick off the mercury. Basically, the net result of this whole bottom row is this molecule kicks off the mercury and replaces it with the hydrogen. You just do it by adding the hydrogen first, making this unstable resonance structure, and then kicking the mercury off. That's just saying that you lose, anytime you see in a mechanism, you see minus something, just means that it leaves. Mostly because organic chemists don't really care about anything that's not our organic molecule. So it would be more accurate to do plus H2 plus. But if we just don't want to write it anymore, we'll just write minus, just means the leaving group leaves.
do that a lot in biochemical pathways because you'll have like waters coming and going all over the place. And instead of continuing to draw them to keep it balanced, you just say minus H2O. Because you're in an aqueous environment, so. What does it matter where the water is, because it's just not attached to our molecule anymore.
That's not what we're doing.
This one doesn't really have a name. And for the most part, I'm not gonna worry too much about the names in general. I don't care really if you know this is called the mercurium ion. The name is just in the figure, so I don't think here. Yeah. If you look up the alkyne, hydration of alkynes. With mercury, you should be able to find things that way. And what, like I said, this is not truly our final product. This is the hydration product of one of the pi bonds, right? Thing is, this is called an enol because chemists sometimes are not creative with their names. It's an enol because it's an alcohol attached to an alkene. Enol. Enols are not super stable. They rearrange themselves. And it looks basically, if you draw out all of the structure, it actually kind of makes sense. And this is actually one where it can be acid catalyzed or base catalyzed. Acid catalyzed is a little bit more common. And they call this process where we're making a different isomer of the same, with the same atoms, basically. And it's an ongoing equilibrium process. They call this tautomerization.
It doesn't sound like work.
And actually, if you type that into Word, I believe it gives you a red squiggly. But I believe it comes from the same root as tautology in math. Tautology is just something that's true because it's true, right? It's true by definition, like 1 = 1 is a tautology. In this case, a tautomerization means that we didn't really change anything and we could change it back. It's the same thing we ended with, we started with, we just with some bonds in different places. And so if it's acid catalyzed, basically the first thing we do is we actually protonate this, because if we have an alkene and acid, we protonate it, right? And that gives us a positive charge on a carbon next to an oxygen that has a lone pair. So this actually isn't very stable. This version of the resonance structure isn't very stable because we have an incomplete octet. And since we have lone pairs right next to it, we just wind up making an extra pi bond. But now the oxygen has 3 bonds. And if the oxygen has 3 bonds, it's got a positive charge, and oxygen with a positive charge, we can do better. At least everything's got a full valence. But it just means that this hydrogen is a really good leading group. So proton transfer to protonate the pi bonds. Makes a resonance structure where we've got a protonated carbonyl, and then we just kick off the proton. So basically, an enol will almost always rearrange itself to be a carbonyl. And the base catalyzed mechanism looks pretty much the same thing. The only difference with base catalyzed tautomerization is you start by deprotonating the alcohol first. And then you turn the extra electrons on the oxygen into the bond here. And that gives you a negative charge here. So then you protonate the second carbon. So it just changes the order of the steps. You either protonate first and then deprotonate, or you deprotonate and then protonate. We see this with aldehydes as well. If we wound up with an enol at the end of a carbon chain, the enol at the end of the carbon chain, when it rearranges, it's not a ketone, you get an aldehyde, but it does the same thing. And this is an ongoing process, actually, any ketone or any aldehyde is actually constantly going through this tautomerization. So you actually have a measurable amount of. We always just call it acetone, but acetone is always in a equilibrium process. That looks like. This, if there's any amount of acid or base. In the solution. Just for the most part, it's more stable as the carbonyl. I would say at room temperature, if you have acetone in water, it's something like 85 to 15. But there's a measurable amount of it like this. All right, so our net results, the whole point of going through that is that our net result of hydration. Oh, we did use hydration. I thought we put that one out. So hydrochloration does the same thing. We make the enol, the anti-Markovnikov enol, and then it rearranges to make the carbonyl. So our net result of hydration of an alkyne is going to be a carbonyl, not an alcohol. Right, and this mechanism, this reaction is the same. Same products and reactants. The other, the Markovnikov hydration, we kind of had to combine the acid catalyzed and the mercury. So we're down to only two options to hydrate alkynes. We have Markovnikov and anti-Markovnikov still though. And the way that we would write the reaction for Markovnikov, it's usually HgSO4, H2SO4. Because it's still the acid catalyzed and you need mercury too. So they usually wind up using mercury 2 sulfate because then you have the same conjugate base for both of these. You have the same anion for the acid and the and the second step doesn't really require, it doesn't really have two discrete steps the way that it does here, like with the oxymercuration and demercuration. Because if you do it in the presence of mercury 2 and acid, you can do it all at the same time. Although you may notice that our second step for the hydrochloration is under basic conditions, not acid conditions. So we're gonna have the reverse of that tautomerization mechanism. So let's try drawing this mechanism just for practice mechanism. We did the acid catalyzed tautomerization. What would the base catalyzed tautomerization look? What's the first step gonna be?
which is then naturally gonna have a resonance structure. Where these extra electrons move down that way, but to do that, we have to make room by moving these electrons over. So usually we put the resonance structures in brackets. And make sure you use the double-sided arrow to indicate that this is a resonance structure. And then we're under basic conditions, but we still have, we just made a water molecule, so we know that there's some amount of water around, right? Or the net result of. Now. So the net result of both of these hydrations is substantially the same. You're turning an alkyne into a carbonyl. It's just, is it Markov-Makov or anti? And then if you're drawing the mechanism, you then need to think about, okay, is it the acid catalyzed version of the tautomerization, or is it the base catalyzed version of the tautomerization? They're substantially the same. The two steps are just reversed. Because under basic conditions, you have excess negative charges floating around, so you're going to wind up seeing mostly negative charges throughout. Acid catalyzed reactions are the opposite. You have an excess of positive charges because you have extra protons. And so you're going to wind up with your intermediates and your resonance structures with positive charges instead of negative charges. That's the same basic idea in both cases. Protonate, deprotonate, you're there.
Cause I look at this as this constructor, pylon forms with R and C, and that pylon.
So that the R is not really gonna get involved in it because the R in all likelihood is sp3 carbons. And sp3 carbons can't get involved in resonance structures because they don't have spare electrons, right? So I would avoid that. There certainly could be some cases where if you had, like, if the R group was a benzene ring, where you could have some other resonance things happening. But you don't want to count on that. This is the standard way. It works all the time.
So that pi bond, the double bond, there's the unhybridized p orbitals. So you can think of
Correct.
it as like the electrons going into that.
Right.
I think that's how I got it. It's simple.
All right, and just so that it's in the slides, I have the cleaner mechanism. There we go. Drawn up. Deprotonate resonance structure protonate. And so even though technically this is the end of the hydration, we did hydrate one of our pi bonds, we added a water molecule, it doesn't stop there. Just like we never stop our mechanisms with a charged molecule, we always show that last proton transfer or whatever to make it the more stable molecule. Same thing here with the tautomerization. All right, so let's do practice of these. Both of these start from a 7. Again, if I ask you this question on a quiz or on a test, you don't have to show all your intermediates, it's just a good way, just like with algebra. Until you're comfortable to start doing the steps in your head, it's a good idea to show your work. Once you get to second year calculus, I'm less interested in you showing every single step of algebra, right? Because I assume you know how to do it. Don't assume you know how to do these yet. So first step, we make the acetylide. Second step, we use it as a nucleophile on methyl iodide. So after step 2. We've got propine. Then we're doing, so the difference in the way that they usually write, we see this, the hydroboration written, a lot of times you'll see R2BH. Just so it's not a 3-to-1 ratio, the boron only has 1 hydride to give. In this case, so, and you can actually buy the molecules, the compounds like this, so that it makes the stoichiometry simpler. But same basic principle, we're just not gonna make that tri-alkyl or hydride with it. And especially with the alkynes, because the alkenes and the rearrangements and pi bonds that are still remaining can really throw that mechanism off. So with the alkynes, we'll usually see it written this way. That's the same mechanism. So then anti-Markovnikov followed by the reduction. So we're going to add our oxygen here. So the enol would look like and then it'll rearrange itself to give us propanaldehyde. Propanal. But we haven't learned how to name those yet, so that doesn't really matter that much. Same first step. Except then we're adding ethyl iodide instead of methyl iodide. I guess questions about the first one.
Would there be a charge on one of these guys since you should pick up on?
Not at the end, because the charge disappeared when we used it as a nucleophile, because we've got plus I minus. Your leading group leaves and takes the charge with it. Second step on the bottom one. We're adding 2 carbons instead of 1. Just ethyl iodide instead of methyl iodide. And then we're going to the acid catalyzed mercury to the Markovnikov hydration. So we put on more substituted. And this is where if we did wind up changing our nucleophile, you could have a different nucleophile for that last step, like we saw with the hydrations with alkenes. We don't really see that at all with the anti-Markovnikov, but we could switch out our nucleophile with the mercury catalyzed hydration to make something other than an alkyl there, but we're not hardly going to see that because of that enol rearrangement. We're mostly going to see oxygen use there. And then Markovnikov hydration, our enol then is going to look like so here's our ethyl group. We added our OH right here. The more substituted carbon, which then rearranges. And we'll get butanol. Similar pathways. The two wrinkles here are changing out your alkyl iodide from methyl to ethyl, to add 2 carbons instead of 1. And then anti-Markov-Makov hydration versus Markov-Makov hydration. So extra wrinkles, but really very similar to what we've been doing. Biggest difference as far as a synthesis tool is the fact that we can do this now and build these molecules up however we want to. Questions?
Is this molecule getting protonated at some point?
This one?
Next one.
Yeah, so this is under acid conditions, so the first step of this rearrangement is protonate here. Which then leaves you with a positive charge here, which makes a resonance structure with the lone pair from the oxygen to make a protonated carbonyl, which then deprotonates. Look at that, we only added 1 new mechanism, really.
Any tips for memorizing all the arrow pushing on the mechanisms? Write it out a billion times or?
Practice, it'll start to make sense. I'll say the same thing that I told everybody else earlier. My lowest test score I ever got on a chemistry test was, at least until grad school, was when I thought I understood how to work out mechanisms on the fly, but I didn't understand it well enough. So they'll start to make sense, just don't fall into the trap of, I'm just gonna work my way through the logic on the test.
Sure.
Yes, you'll get to that point, but I started this off by writing out a mechanism that I mixed up one of the arrows. So it's a lot. Start to remember patterns. Remember what are the steps, and I guess the other thing is give yourself landmarks. Like, okay, you don't need to memorize every arrow. If you remember, okay, this is gonna go to a carbocation. How do I make a carbocation out of this? And then from the carbocation, I know I'm gonna have a nucleophile attack where I'm gonna have a rearrangement. How do I draw the arrows for that? Memorizing, using those as your landmarks makes it a lot easier. And when you're given directions, you don't need to give mileage for every single street, as long as you say, when you see the McDonald's, turn right. And you just need to know where the McDonald's, that you're gonna get to the McDonald's at some point. And then you don't say, it's 13.2 miles.
Which is oftentimes less useful than saying turn right at the McDonald's.
Exactly, yeah. So look for the patterns, look for the landmarks. All right, so there will be a quiz this weekend, because we actually did get through everything I wanted to get through, despite having the short lecture on Tuesday. So we're actually still on schedule, maybe more on schedule than I've ever been in this one. How about that? Other than that, have a good weekend, and then next weekend we'll do the Norbornene lab. Or next Tuesday. Mostly, I'm gonna go home and sleep.